Okay, we're going to work through differentiation from first principles. I'm going to look at the theory and then we're going to try an example as well. I'm going to start off with my set of axes here and draw a really general curve. This curve could be anything at all that you're familiar with. Y equals x squared, y equals x cubed, y equals 3x to the power of 5 plus 4x to the power of 4 plus 3x to the power of 3. You get the picture. It could be anything. So there's my x and y axes. And there's my really general curve. It's y equals fx. It's some function of x. There's a point P on the curve, and there's a tangent through P on the curve. This is going to become important later. There's another point Q on the curve. Now if I draw a line through P and through Q, I don't have a tangent, but I've got a secant. We could calculate the gradient of that secant, and that's what we'll do. One of the purposes of differentiation from first principles is to look at the gradient of the tangent through P. Now, so that this process can work properly, what I want is to make sure that the interval between P and Q is as small as possible. And the reason for that is that the closer that Q gets to P, then the more the secant through P and Q looks like the tangent just through P. Now my Q's move towards P there. Slight problem though with my animation here. The secant, the red secant there, probably should have moved as well. Okay, that needed to move so that it would look more like the gradient, would look like it had the gradient of the orange line, which is the tangent. So my Q has approached P. The gradient of my secant, in other words, which is there, gets closer and closer to the gradient of the orange line, which is my tangent. And in mathematics, we use the arrow to mean approaches. MPQ means the gradient of PQ approaches the gradient at the point P on the curve y equals fx. Now, those two things are true. That statement is true, that the gradient of PQ approaches the gradient at P, as long as the distance between P and Q gets increasingly smaller. We're going to actually give our points coordinates now, or they're going to be very general. P is the point now with the x coordinate x and the y coordinate f of x. And Q is the point x plus h, f of x plus h. Now where did that come from? Well, all that's saying is that the distance along the x-axis between P and Q is a distance of h units. In other words, if P is at the point x, then Q is at the point x plus h. Now, similarly, if P is the point along the y-axis of f of x, then the distance vertically up to Q is f of x plus h. Now, this is generally the way that the coordinates are written when one's trying to differentiate by first principles. Very similar to the way in which textbook exercises do it. There are other methods, but this is the method we'll stick with today. Using that letter h to represent the distance between P and Q on the x-axis, so see here with my cursor I'm pointing to the x-axis, so here is approximately where on the x-axis P is, and if we go a little bit further along, then you find Q. And the distance between P and Q on that x-axis is h units. H approaches 0 means that the distance between P and Q along the x-axis approaches 0. So from here to here, that approaches 0. The closer and closer P and Q get together. Alright, so let's put all of that notation into some sort of formula. We already know that the gradient equals the rise over the run, and that's the difference between the y values divided by the difference between the x values. Okay, y2 minus y1 over x2 minus x1. And this is the reason why it's difficult without calculus, or impossible without calculus, to talk about the gradient at a point. And that's what we're interested in doing with calculus with respect to curves. We want to find what is the gradient at a point on a curve. The reason why we've got straight lines here is because we can use the gradient formula to define what the gradient is for a straight line. The only way it's going to make sense for a single point on a curve is when the 2 points that we're interested in are extremely close together, as close as you like, infinitesimally close together. I'm going to define something therefore called the gradient function. So it's not the gradient as a single value now, but the gradient will have a different value at different points along the curve. We can see on my blue curve here, at the point P, the gradient looks relatively steep, but up here near Q, the gradient seems fairly flat. In other words, the steepness of the curve isn't very great. As we move away from Q and we head back down the other side of the curve, the blue curve, what we find is the gradient turns negative. In other words, the gradient's changing at each point along the curve. So rather than it being a single number, the gradient is going to be some function of x. As you move along the x-axis, the gradient will be changing. We said the gradient's a function of x. And that's why we're using this new notation. This notation is due to Gottfried Wilhelm Leibniz. And Leibniz used the letter D because D stands for difference. The difference in the y values divided by the difference in the x values. And as I've said there, it's simply new notation. Okay, so regard it as being analogous to the letter M when we're talking about straight lines. It's the change in y with respect to x, or simply the gradient function. Okay, this is a formula that I was somewhat reluctant to put in, but I thought it'll make things a little bit clearer. You don't see this generally in textbooks, but it'll emphasize what's to come. And the gradient function is equal to the limit as h approaches 0. In other words, as that distance along the x-axis between P and Q gets ever smaller as it approaches 0, then we're interested in finding out what the gradient of that straight line from P to Q is, because that will approximately be the same as the gradient exactly at P. Indeed, as h approaches 0 and effectively equals 0 because it's so infinitesimally small, the gradient of the straight line PQ will be the gradient at P. And if we want to calculate the gradient from P to Q, then we can use this gradient formula, y2 minus y1 at x2 minus x1. But the coordinates of y2, y1, x2 and x1, which we defined on the previous slide, are slightly different to what we're used to. They're the x, fx, they're the x plus h, f of x plus h. So I just wanted to emphasize there that the gradient function comes from a limit formula. It's a limit, the gradient function. And as I say here, we want a formula for the gradient of the tangent to the curve at the point P. And this is the gradient of the secant between P, x, fx, and they're the coordinates of P, x, f of x, and Q, x plus h, f of x plus h. And when the difference between them along the x-axis is infinitesimal, then this formula will work. So now I'm going to sub in those coordinates here into this formula. So this formula here that's appeared now is one step prior to the formula you'll get for differentiation by first principles in the textbook. And the way that you get this formula is simply to take this formula here and to sub in the coordinates for P and the coordinates for Q. If you let y2 and x2 be the coordinates of Q, and x1 and y1 be the coordinates of P. Okay, so what is y2? Well, y2 is f of x plus h. And what's y1? That's f of x. And similarly on the denominator here, you can see x2 is x plus h, and x1 is just x. We can simplify the denominator, remove the brackets, the x's cancel to leave you with nothing but h down the bottom there. Now, for those of you who are a step ahead, you might realize that, well, you can't simply substitute h is equal to 0 into this formula because you're not allowed to divide by 0. It's against the law. Well, it's against the law of maths. You can't divide by 0, and so what that means is that when we do the algebra for a specific curve and differentiate by first principles, you'll find that it will always be the case that the h on the bottom will cancel with a factor on the numerator. We'll see that in an example that we do shortly. But before that, we might just recap using the derivation for that formula we've just found without the graph. So once more, remember our x1 value is simply x, while our x2 value is just a little bit bigger than this, namely x plus h. What's h? Well, h is a number as close as you like to 0. This means that the two y values will be f of x and f of x plus h. Our gradient formula, y2 minus y1 over x2 minus x1. It takes on a slightly different form when instead of talking about the gradient, we talk about the gradient function dy dx. So instead of the letter m, we're now going to use dy dx. And once more, the reason for that is because m, when we're talking about straight lines, equals a single number. M is equal to 2 or minus 4. It's equal to a constant number. But with curves, it won't be. There'll be an x involved. So it might be 2x or 3x or 4x squared. It'll be a function of x. So that gradient function is going to be defined as a limit as h approaches 0 of the gradient function of the gradient formula. There I've substituted in x1 and y1 and x2 and y2. They're the coordinates of P and Q. A little bit of simplification on the denominator leads to the formula that you really need to commit to memory. This is the formula for differentiation by first principles. And what you can notice is the formula still looks like a rise over a run. The top of that formula is still the difference between the y coordinates, and the bottom is still the difference between the x coordinates. Okay, time for an example. We're going to start with the parabola. That's the place that I think most teachers start, just looking at the most simple case of a curve, y equals x squared, and I want to find the gradient of a tangent at any point on the parabola. There's my parabola, and I want to know what is the gradient of a tangent there, or really, perhaps I want to know what the gradient of a tangent, say, there is, or maybe even the gradient of a tangent there. Looks like that green tangent probably has a gradient of 0 by the look of things. We need to know, is there a single formula for this particular curve, y equals x squared, that will be able to tell us what the gradient is at any point on that parabola? And that's our purpose. Well, what is the gradient of a tangent drawn at any point on that parabola going to be? Is there a relationship between the gradient of the tangent drawn and the x value, where the tangent intersects the curve? A word that you're going to become increasingly familiar with is this idea of differentiation. To differentiate a curve means to find the gradient function given that curve. So differentiation will give us a formula for this parabola that will be able to generate the value of the gradient for the tangent to any curve. So we're not just going to stick with y equals x squared, we're eventually going to look at more general cases. Okay, so we've already generated a formula to enable us to differentiate by first principles. And now we're going to try a specific example and calculate the gradient function, which we're going to call dy dx or dy by dx, for a particular function. And we're going to use y equals x squared. And the process we're going through, often referred to as differentiation, a word you're going to become familiar with increasingly over time. Now for the case of y equals x squared, the parabola, we're going to not use y anymore, we're going to use f of x instead. And our f of x is going to represent x squared. So in the gradient function formula over here, wherever I see an f of x, I'm going to sub in x squared. And well, our function notation shows us that if the function of x is x squared, then the function of x plus h must be x plus h all squared. Okay, so I'm going to be able to sub in two things on the numerator here in order to eventually derive what my gradient function will be. So let's see our first step here. My f of x is x squared, and my f of x plus h is x plus h all squared. Okay, if f of x is x squared, and I want to know what f of x plus h is, then what I need to do is to find wherever there's an x, to substitute an x plus h. Now I'm going to expand this bracket here, and so I've expanded x plus h all squared to become x squared plus 2xh plus h squared. I've still got my x squared left at the end there, and so in the next line that'll become important, where the x squared here, as a result of my expansion of x plus h all squared, and my minus x squared here have effectively cancelled each other out, and I'm left with 2xh plus h squared, and that's all divided by h. And my next line is where I've taken out a common factor. I really should have included an extra line there, but for those of you who are able to follow me, you'll see that, well, h appears in 2xh and h appears in h squared, and so my h on the bottom can divide through the numerator, leaving me with nothing but 2x plus h on the top there. And the h on the bottom has cancelled with that h, and it's cancelled with one of these h's. Because h approaches 0, I'm left with nothing else but 2x. Okay, we're going to try another example here. It'll be text up on your screen at the moment, which basically explains what we're about to do, which is differentiate y equals 4x cubed minus 3x from first principles. We've already differentiated y equals x squared, and we just want to recall that to differentiate is to find the function which, when we substitute the x value into it, it will give us the value of the gradient of a tangent at that point on the curve. If I was to use the letter m, then m equals 2x is the formula for the gradient of a tangent to y equals x squared at the point x. I don't normally use the letter m though when we're talking about the gradient of curves, okay, because m normally stands for a constant, and so for that reason we don't use m, instead we use new notation, which is dy by dx, or dy dx. Okay, there's my formula. Once more, it needs to be committed to memory so that we can begin doing this question. Okay, so I probably should have written up there what one we're doing, but we can tell from here that what I'm trying to do is to differentiate y equals 4x cubed minus 3x. Okay, so that's my purpose here. The reason I haven't got it written up there though is because it simply won't fit into the slide. You'll notice that a few of these questions that you do require a lot of space. You know, you're going to be looking at half a page to a page of working sometimes, depending upon how many lines of algebra you can do in your head. Okay, so let's begin this one. We're subbing in for f of x, this here. we also need to put in f of x plus h. So f of x plus h is the formula that you get when you put x plus h into the spots in f of x wherever you see an x. So here I see an x and here I see an x. So I'm going to put x plus h next to the 4 and cube it all, and I'm going to put an x plus h next to the 3. And so I've got a 4 x plus h, or cubed, minus 3 of x plus h. And that's my function of x plus h. From that, I'm going to subtract my function of x. And that's how I get my numerator. It's all divided by h. Let's expand the brackets. Okay, so here we've used the fact that the function f of x is equal to 4x cubed minus 3x, and so f of x plus h equals 4x plus h cubed minus 3x plus h. Okay, so what's happened here? To be careful, I've noticed that students seem to think sometimes that although we know how to expand something like x plus h all squared to get x squared plus 2xh plus h squared, that when it comes to cubing x plus h, they'll immediately just put a 3 above the x and a 3 above the h to get x cubed plus h cubed and think they're done. Or that there's some formula, indeed, for expanding x plus h all cubed. There is, but we don't need to use it. Instead, what we do is we just split the x plus h all cubed into x plus h times x plus h all squared. Okay, so that times that gives me that. That just helps us do the working. That's the only thing that I've done to get to that next line. And to get to this line, well, we know how to expand x plus h all squared, and that becomes this. I've expanded this bracket here to get 3x minus 3h. And we can further expand the brackets, and we end up with something that looks rather ugly. X times x squared gives me x cubed. X times 2xh gives me 2x squared h. X times h squared gives me xh squared. H times x squared is x squared h. H times 2xh is 2xh squared, and finally h times h squared is h cubed. Check to see you can get to that line from this one. Finally, the 4 has multiplied through every single term there. I've also removed the last bracket here, just be aware of that. Minus times a minus gives me a plus here. Collect like terms. It's an easy step, but you need to be careful to ensure that you do pick up all the like terms. You might want to think, rather than watching this straight through, I hope you're pausing at particular points. Now might be a good time to pause. Can you simplify from here on? From this point onwards, what do you do? I've factorized. I've taken out a common factor of h. You should always be able to do that. In any of these differentiation by first principles problems, there should be a common factor of h that comes out. And the reason for that is that we need the h on the top here to cancel with the h on the bottom. If it doesn't, then we can't evaluate our limit, not in any trivial way anyway. If our limit approaches 0, then if this h is still there, we're dividing by 0. Once again, you're not allowed to. It's against the law. It's just not logically possible, actually. So I've cancelled my h on the denominator there. and because it's a limit now, I'm going to regard as being 0 any term left that contains a h. Okay, so 12x times h, which is 0, and 4 times 0 is also 0. So my 12xh, that's going to vanish, and my 4h, that's going to vanish, leaving me with, well, what? 12x squared minus 3, and so that's my answer. I can just write, I can remove the limit notation now. There's no reason for me to continue saying if the limit as h approaches 0, there is no longer any h there, the h is dropped out. So my final answer is generally written as dy dx equals 12x squared minus 3. And so we're done.